Honorable judges, we're from Team 238. Today, we present our project titled Design and Optimization of an Integrated CO2 Liquefaction LNG Regasification Process to support the CCS Hub Storage Network.
Liquefied natural gas contains a large amount of cold energy due to its low storage temperature of around minus 162 degrees Celsius. Carbon capture and storage consists of CO2 capture, transportation, and storage. Before transportation, CO2 must be compressed and cooled so that it becomes liquid. The liquid phase allows the large quantity of CO2 to be transported efficiently. During transportation, CO2 is not converted into the solid or supercritical phase because the loading and unloading process will be very difficult. Transportation in pressurized liquid is already well established, similar to the liquefied petroleum gas carrier. However, the energy consumption for the compression and cooling in the CO2 liquefaction process is a major contributor to the operational expenses. Therefore, our proposed solution here is an integration of CO2 liquefaction and LNG regasification process. This research was conducted using Aspen Tech 314 and MATLAB software. The independent variable is CO2 outlet pressure. The control variables are West Java FSRU, LNG capacity, CO2 inlet composition, CO2 inlet pressure, CO2 inlet temperature. The dependent variables are the amount of CO2 liquefied, the amount of energy consumption, and the total annual cost. Okay. We perform simulation in Aspen HYSYS using three compression design scheme, which represent the distribution of CO2 outlet pressure based on displayed on the screen. For this flowsheet, we use one compression system, and next we use the two compression system, and the last we use the three compression system. Next, for the optimization methodology, we implement using MATLAB. This step was used to determine the optimal operating condition by analyzing the trade-off between total annual cost and liquefied CO2 production. Here, we conduct the distance to ideal point and key point method for the optimization.
Okay, from the Aspen HYSYS simulation result, we observed a trade-off between CO2 liquefaction capacity, energy consumption, and economic performance. Increasing CO2 outlet pressure improves liquefaction capacity. However, it also increases energy consumption. Higher outlet pressure leads to higher capital and operating costs due to increased equipment specifications and energy demand. As a result, total annual cost also increases. To address this trade-off, multi-objective optimization was performed using MATLAB. The objective was to maximize the amount of CO2 liquefied while minimizing total annual costs. Using both the distance to ideal point and any point methods, the same optimization result was obtained at a CO2 outlet pressure of 13.68 bar. And for the conclusion, an LNG-assisted CO2 liquefaction process was developed and simulated using Aspen HYSYS. Three compression scenarios were evaluated, showing that increasing CO2 outlet pressure improves liquefaction capacity, but significantly increases energy demand. And the optimal condition was achieved at 13.68 bar, producing 126,326.66 kilogram per hour of liquid CO2, with a total annual cost of 78.19 billion Indonesian rupiah.
The study confirms the potential of LNG cold energy to enhance CO2 liquefaction efficiency. By leveraging existing LNG regasification infrastructure, this approach provides a practical pathway to support CCS hub development with improved energy utilization and optimized cost performance. Thank you.